section 2.3, dealing with continuity. So we'll start with discussing continuity at a point and continuous functions. We'll touch a little bit on algebraic combinations and composites, and we will discuss the intermediate value theorem. We start with continuity at a point, and we start with the definition that the book provides. So let's take a look at that. Here we have continuity at a point, starting with an interior point on an interval. So let's think about an interval from A to B, and let's say it looks something like this. And we have something that looks something like that. All right, so it says a function y equals f of x is continuous at an interior point, C, of its domain if the limit as x approaches C of f of x equals f of C. So they're saying C is within the interval from A to B, and the function is continuous if the limit as x approaches C is equal to f of C. All right, so there's an example of a continuous function as I approach from the right and from the left, getting closer and closer to C. Both the left and right limit approach f of C, and the function value is f of C. So this function is continuous on an interior point. The way I think about this, when I think about continuity at a point, I break it into three things that I must consider. First, I must consider whether or not the limit exists. For it to be continuous, the limit as x approaches C must exist, which means that the left limit must equal the right limit. Secondly, the function value must exist. That means f of C must be defined. And finally, the two must be equal. The limit as x approaches C of f of x must equal the function value f of C. So anytime I'm dealing with a problem where I'm asked about the continuity at a point, I address it in this way. I first check to see if the limit exists, if the function exists, and then if they are equal. So the informal way to think about a function being continuous on an interval is to think about the fact that I can trace a function without lifting my pencil. If I need to lift my pencil to trace the function, then it is not continuous on that interval. That's the informal way to think about it. Now, the second part of the definition deals with the whether or not the function is continuous at an end point. So what we need to consider here, if we think about whether or not we are continuous at the point x equals b, well, the same three criteria apply, but when we do the limit, we can only approach b from the left. So if we were interested in whether or not the function is continuous at x equals b, we would first say, does the limit as x approaches b from the left exist? Does the function value exist, f of b, and are they the same? If we then were interested in whether or not we are continuous at x equals a, then this time when we evaluate the limit, we would only be looking at the limit from the right, because we have no information about the left. All right, now looking at these 6 graphs, we want to easily determine if they are continuous functions or discrete functions. Discrete functions really represent a collection of points. So our first graph is continuous, our second is continuous, and the rest would be discrete because I need to pick up my pencil to trace those functions. Okay, so let's apply this information to our first example. which says to find the points of continuity and the points of discontinuity of the greatest integer function. Well, we need to remember the notation for the greatest integer function. Generally looks like this, and this means y equals the greatest integer that is less than or equal to x. So if I were finding the greatest integer function, or the greatest integer of 4.5, I would ask, what is the greatest integer that is less than or equal to 4.5? And that would be 4. Then if I tried the greatest integer function of 5, that is the greatest integer that is less than or equal to 5, that would be 5. So you can see from the graph, and you should note in this book, greatest integer function is written as the int of x. That's another way to write greatest integer function. But you can see that this function is clearly not continuous everywhere. We have these jumps going on, and we do have some intervals that are continuous. So we would say y is discontinuous at all integers. So you can see that is where we have our disconnect in our graph. And then we could say that y is continuous at all other real numbers. Those being the ones that are not integers. Okay, so let's move on. All right, so there are 4 different types of discontinuities that we deal with. A removable discontinuity, and we should note that the other 3 are all considered non-removable discontinuities. And we'll start by defining what a removable discontinuity is. And we get a removable discontinuity if we can change one point and the function would then be continuous. So if we can change one point and the function would then be continuous, then that discontinuity is called removable. So the basic idea is for a removable discontinuity is something like a hole. So if we look at graph C, we have a line, y equals f of x, with a hole at x equals 0 and a function value of 2. So if we were to just somehow be able to change that function value to be 0, this function would then be continuous. So this is an example of a removable discontinuity. All right, now we have 3 types of non-removable discontinuities. And graph D is the jump, also called a step discontinuity. Graph E is an infinite discontinuity. So that's when we run into an asymptote. And graph F represents an oscillating discontinuity, which tends to be one of the more difficult discontinuities to understand. First off, we need to understand that this graph does not stop here on the x-axis. It continues to bounce back and forth, pardon my drawing, but it continues to oscillate back and forth between 1 and -1, everywhere in between, where those two blue parts of the graph stopped. Now, let's think about why this would be called a discontinuity. Well, if we are continuous at a point, three things must be true. The limit must exist, the function must exist, and the limit must equal the function. Well, let's look at whether the limit exists at, let's say, x equals 0. Well, if we go back to the definition of a limit, I should be able to move to the left and right of 0 some delta amount, or some amount less than some given delta, and go up to the function and stay within the red zone, within epsilon units of my limit. So if I think about x equals 0, if I move to the right some small amount, and go up and over, then I could be within a small amount, epsilon, of 1. But if I were to go to the left, I would no longer be up towards 1, but I would be down towards -1. And I would be able to stay within epsilon units of -1. And it would continue to bounce back and forth between 1 and -1. So by the definition of the limit, there is no existing delta such that I would stay within epsilon units of a given limit, because this function keeps bouncing back and forth between 1 and -1. So that's a quick explanation of why this type of function is called an oscillating discontinuity. We may get back to this exploration on block day, so we're going to skip this for now. Okay, two terms we need to be familiar with. We will refer to a function as being continuous if it is continuous at every point, and this got cut off, at every point in its domain. So if we think about the function f of x equals 1 over x, the domain for this function is x equals all real numbers such that x does not equal 0. So x equals 0 is not in the domain of this function. Well, let's think about the continuity. I am continuous everywhere except x equals 0. But because x equals 0 is not in the domain, 1 over x is considered to be a continuous function. Because it is continuous at every point within its domain. And then finally, a function is continuous on an interval if and only if it is continuous at every point in the interval. This idea is the tracing with the pencil idea. If I am able to trace the function in the interval without lifting my pencil, then it is continuous on that interval. Okay, example 4 pulls in some properties of continuous functions. And what we have to realize, some of the properties that hold, if we look at x sine x, so this problem says show that y equals the absolute value of x sine x over x squared plus 2 is continuous. Well, let's look at x sine x, break it into its parts. X is continuous, and sine x is continuous. So the product, x sine x, is also continuous. All right, let's look at x squared plus 2 and the property of addition and subtraction with continuous functions. So if the terms that are being added and subtracted are continuous, then their sum or difference is also continuous. Here we have x squared is continuous, and 2 is a continuous function. So x squared plus 2 is continuous. All right, so let's go one step further. If we have x sine x over x squared plus 2, the numerator is continuous and the denominator is continuous, and the denominator cannot equal 0. So the quotient of the two is a continuous function as well. All right, so finally, let's see, we've looked at products, we've talked about sum and difference, we've looked at quotient, and now let's consider calling g of x the absolute value of x, and f of x is x sine x over x squared plus 2. So the function that we are dealing with, our y function up here, is actually g of f of x. It is the composite or composition of our two functions. We've shown that f of x is continuous, and the absolute value x is also a continuous function. So the composition of the two, absolute value of x sine x over x squared plus 2, is also a continuous function. All right, intermediate value theorem is a basic idea that we've used before in mathematics, but it becomes very useful in a lot of problems that we deal with in calculus. And the basic idea of the intermediate value theorem for continuous functions is, if a function is continuous, on the interval, let's say a to b, then there must exist some point c, some x value c in the interval a to b, such that f of c, or in this picture, w, falls between f of a and f of b. So the basic idea is, if the function is continuous on the interval from a to b, I cannot get from f of a to f of b without going through every single y value between f of a and f of b. This is useful in problems like determining if we have a 0 between two y values or two function values. So if I am on the interval from a to b and I'm given some function, let's say we have x squared plus 2 on the interval from a to b. Well, x squared plus 2 is a parabola shifted up 2, like that. Well, we would want to know if, on the interval from a to b, if there is a 0. And we could test this. X squared plus 2 is a continuous function. And if we want to figure out if there is a 0, we could check to see if f of a is a positive or a negative value. And then f of b, check to see if f of b is a positive or negative value. If we see a sign change, then we know that there would be a 0 between f of a and f of b. There would be a 0 between the interval x equals a and x equals b, because we would see a sign change. So x squared plus 2, we would not see the sign change. Positive we would get for f of a, and we would also get a positive for f of b. But if I had a function like just a simple line, sorry for my crooked lines, let's say I had this line, and I am on the interval from here, a to b, and I know that f of a is negative, and I know that f of b is positive. By the intermediate value theorem, I could say that there is guaranteed to be a 0 in between. Because the line is a continuous function, there has to be a point, I'll call that point C, where it crosses the x-axis. So, this is the basic idea of the intermediate value theorem. All right, homework for tonight is on the assignment sheet on the website, page 84. And you should note that we have a quiz on block day covering 8.3, 2.1 through 2.3. And I will be in after school on Tuesday and before school during tutor time on Wednesday before the test. I will be here after school Wednesday as well. So these are the times you can come in for extra help to get ready for your first quiz. Let's take a look at a few examples. I wanted to do some examples from the homework so that you had video of these to help you get through the rest of the assignment. So let's look at number 19. In part A, we have to find each point of discontinuity. And part B, which of the discontinuities are removable, not removable, and give the reasons for your answers. Well, if we want to find the points of discontinuity, we need to look at the function itself. Our f of x is a piecewise function. And 3 minus x is just a line, so that is continuous, and our function is defined to be that when x is less than 2. And x over 2 plus 1 is just another line, and our function is defined to be that when x is greater than 2. All right, so if we are interested in continuity, our first branch up here, 3 minus x is a continuous function. X over 2 plus 1 is a continuous function. So really the only possible place we could have a discontinuity is at x equals 2, where the branches differ. So let's take a look at the 3 things that need to be true for us to be continuous at a point. First off, the limit must exist. Well, that means we need to look at the limit from the left as x approaches 2 and the limit from the right as x approaches 2. So we'll take a look at the limit as x approaches 2 from the left of f of x. And to do that, we are just going to plug 2 into the top branch. 3 minus 2 is 1. And let's take a look at the limit as x approaches 2 from the right of f of x. And that would be 2 over 2 plus 1. 1 plus 1 is 2. So here the left limit does not equal the right limit, so the limit does not exist. So our function is not continuous at this point because we would have to have the limit exist, the function exist, and they'd have to be equal. So it fails on the first criteria. So now we need to determine what kind of discontinuity we have. Well, let's think graphically what we are dealing with here. Let's see, we have 3 minus x, that's 1, 2, 3, with a slope of negative 1. All right, and our second branch of our piecewise function is x over 2 plus 1, and it is defined to look like that where x is greater than 2. So let's get that one in. So plus 1 would be the y-intercept, up 1 over 2, and up 1 over 2 again. It looks something like this. Turn that the other way. There we go. So this is what our function looks like. And by thinking about it graphically, we can see we have a jump, which is a non-removable discontinuity. So that answers part B. It is non-removable because it is a jump. All right. You should be aware in our book that problems that have this gray background are problems that you are expected to do without your calculator. So I'm going to stop the recording for a minute and put down the work for 20 and 21, so you have that to follow. Okay, so part A in number 20, if you look up here, 20 is another piecewise function. It is 3 minus x if x is less than 2. It is 2 if x equals 2, and it is x over 2 if x is greater than 2. So we first ask ourselves about the continuity. Does the limit exist? So we take a look at the limit from the left as x approaches 2. That equals 1, because that is 3 minus 2. We look at the limit as x approaches 2 from the right. And from the right, we plug in 2. We get 2 over 2, and that is 1. So the limit from the left and the limit from the right are equal. So the overall limit is equal to 1. So the limit does exist. So we would say check here, if I get a better color choice. Okay, so the limit does exist. Now, the second condition or criteria for continuity at a point, does the function exist? Well, it is defined f of 2 is equal to 2. So f of 2 equals 2, the function exists. All right, now, does the limit equal the function? Well, the limit was 1. The function was 2. So the limit as x approaches 2 of f of x does not equal f of 2, so the function is not continuous. Now we have to answer the question, is it removable or non-removable? So we looked at the graph of our piecewise function. We have 3 minus x if x is less than 2. We have x over 2 if x is greater than 2. Notice that fills in the hole. Does it fill in the hole? Sorry. Is there an equal sign? There's not. So that is still we still have a hole there. Let me make that clear on the graph. This is still a hole. And when x equals 2, the function equals 2. That is the red dot. So, is this a removable or non-removable discontinuity? Well, it is a removable discontinuity because if I just simply fix f of 2 to fill in this hole, we would have a continuous function. So this is a removable discontinuity. All right, let's look at 21. All right, if we look at 21, this one, notice, is not grayed out, so we can use our calculator on this one. And I have graphed the piecewise function using my TI-84. Notice that we resemble 1 over x minus 1, where x is less than 1, and we resemble x cubed minus 2x plus 5, where x is greater than or equal to 1. And we should note, and I'll do it in a different color, that there is no hole here. This is a closed dot. Maybe red would be better. Okay, so it looks like that. All right, first off, does the limit exist? Well, we take a look at our functions, and 1 over x minus 1 is continuous everywhere except x equals 1, which is not in its domain. so that is a continuous function. X cubed minus 2x plus 5 is a cubic function, cubic polynomial, and that is a continuous function. So the only place that we could have a discontinuity is where our piecewise function breaks into branches. So we look to see if the limit exists at x equals 1. We look at the limit as x approaches 1 from the left of f of x, and that is going down to negative infinity. Then we look at the limit as x approaches 1 from the right, and that is coming down to a value here, and that value is, if we plug in 1, comes out to be 4. So the left limit and the right limit are not equal, so the limit does not exist. It fails the first criteria of continuity at a point. The function is not continuous. And then based on our graph, we can tell that we have an infinite discontinuity, which is non-removable. Here is the asymptote that is occurring right here. All right. Now, looking at number 49. This is a very common type of problem we see dealing with continuity. We're given a piecewise function. Find a value for a so that the function is continuous. All right, again, for the function to be continuous, the limit must exist. I know you're tired of hearing this, but you're going to remember it. The function must exist, and the limit must equal the function. All right, so on this piecewise function, for the limit to exist, the left limit must equal the right limit at x equals negative 1. So the limit from the left is 4 minus negative 1 squared, which is 3. And for this to be continuous, that must equal the limit from the right, which is plugging in negative 1 to this branch. So 3 will be equal to a times negative 1 squared minus 1. 3 equals a minus 1. So a must equal 4. All right, if that is the case, let's double check. The limit exists. The limit from the left was 3, and now the limit from the right, if I have 4x squared minus 1, when I put in negative 1, that 4 minus 1 is 3. So the limit exists and is equal to 3. The function value is going to be the value at x equals negative 1. So again, we're just plugging negative 1 into 4 times x squared, so that's negative 1 squared minus 1, that equals 3. So the limit exists, the function exists, and they are equal. So if a equals 4, then f of x is continuous. All right. Number 52 is the salary negotiation problem. So it says a welder's contract promises a 3.5% salary increase for each year for 4 years, and Louisa has an initial salary of $36,500. Show that Louisa's salary is given by y equals 36,500 times 1.035 to the greatest integer of t. Well, if we just simply look at y equals 36,500 times 1.035, we have just a nice exponential function, and it needs to be raised to the integer of t because they are not applying the increase throughout the year, just at the end of each year, or at the beginning of each year, one time per year. So if we check at t equals 0, we get 36,500 times 1.035 to the greatest integer that is less than or equal to 0, which is 0. So we have 1.035 to the 0, which is 1. So we get 36,500. So that makes sense. And if we were to look at T equals 4, because she's getting the salary increase each year for 4 years, then we would be looking at 36,500 times 1.035 to the greatest integer function of 4, which will be 4, 36,500 times 1.035 to the 4th. Looking at that, we're looking at a salary of 41,884.59 after 4 years, which seems to be a reasonable approach to calculating her salary. All right, part B says, graph Louisa's salary function. At what values of T is it continuous? So I have graphed our function, y of t, and just so you know, my window has been set from 0 to 5 in the x going by ones, so that's for each year, and then from 36,000 up to 50,000 by 5s. So this is year 1, year 2, year 3, year 4, and year 5. And right here we start at 36,000, and up here we are at 50,000. Just to give you an idea of what we're looking at. So at what values of t is it continuous? So our function y is continuous at all real numbers greater than 0 that are not integers. And I should be more specific because they said that she would receive this salary increase for 4 years. So really, y is continuous at all t such that t is greater than 0 and less than or equal to 4, and t is not an integer. That might be a better way to say it. I think that will do it. Okay, so that is number 49. I believe that's my last example. So all of these problems, these examples at the end, 19 through 21, 49, and 52, all came off your homework assignment, so hopefully these will help you with the other problems you'll be doing in the assignment. All right, so good luck on your homework, and I will talk to you all soon.